My name is James Tompkin, and I'm an assistant professor at Brown University, and it's my pleasure to present the keynote for this algorithms session at DCIO. Today I'm going to tell you about how we can improve our scene reconstruction methods using neural fields techniques. Here's a couple of teasers. Computing the depth of the scene is important for measuring the geometry. We're going to show that the depth sensing from time-of-flight cameras is often in error, and that we can fix this depth sensing, such as on the right-hand side, to produce much more accurate results, lower noise, using these neural field methods. Okay, teaser number 2, we're going to show you high-quality scene reconstruction from photographs, being able to interactively render high-quality appearance for a scene at novel viewpoints to allow us to explore a scene virtually. But before we delve into neural fields, a little bit about myself. As I said, I'm an assistant professor at Brown University, and I think about all kinds of image creation, reconstruction, and editing tasks. When we think about solving visual computing problems, we often think about computer graphics, which is a synthesis task, and computer vision, which is an analysis task. Oftentimes we have a visual scene model that we want to turn into visual data. That's the synthesis branch. And then oftentimes we have visual data, often large scale, that we want to analyze. That's the computer vision part. When you put these into a little cycle, you say, well, it's a bit like a visual Turing test. If I can take images and analyze them to produce some scene model that I can then synthesize with computer graphics to reproduce the input image, if my model is good, then I can do this very well. So we're going to look at lots of methods based around this concept, what you might call a reconstruction loss or reconstruction objective. Given this loop, then I also think about how human beings perceive information, how we can visualize information to human beings in effective ways, and how they can interact in effective ways too. And this helps us with creativity and design problems, understanding the visual world, and of course making predictions about the visual world. Specifically, we think about multi-camera systems, just like those that I showed you at the beginning. And we think about this problem of how we can build capture and editing tools for multi-view images and videos. Now every smartphone is a multi-camera system with all kinds of visible light cameras and these TOF or time-of-flight depth cameras that use active sensing to work out where in the world things are. And these have all kinds of applications for measurement tasks, in industry and design problems, but also in things like virtual reality, augmented reality, and content production. Okay, so here's my little how I think about the world slide. Light travels everywhere and is sampled by cameras, often multi-camera systems, that from this planoptic function of all light produce a 2D map of intensities for how bright the world was from that particular direction. But our true goal is to recover by analysis representations of the geometry, the lighting, and the materials of the real world. These representations are hard to discover. This analysis task is hard because we've lost information in our capture process. But then the synthesis branch takes those representations of geometry, of lighting, of material, turns them back into a 2D image to be displayed, to then be interacted with on a 2D display or even in a VR display by the human being. So we said oftentimes the most difficult part here is in solving this very ill-posed problem of how we can take our 2D camera images and reconstruct these useful representations for our tasks. This has been a problem that's been faced by computer vision for decades, but just in the past 2 years, we've made significant progress using this new set of methods that we call neural field methods. So what is a neural field? Well, the basis neural comes from neural network. Okay, and a neural network is simply a mathematical operation that takes in some values, x1, x2, x3, and then tries to learn how to weight W and bias B these inputs to achieve some task. This is our optimization problem to define the weights that produce the most performance on a particular task. We build networks of these by adding nonlinear activation functions and then layering them to be able to approximate all kinds of different functions. So here is what's called a multi-layer perceptron. We can see 2 layers of neural networks, and each of those arrows is going to have some weight that allows us to combine the inputs to produce some output. We know that neural networks are useful because they are universal approximation functions. Given enough neurons in my network, I can represent any function. This is the universal approximation theorem. So they're very useful to represent all kinds of complicated functions in the real world, often that we care about for reconstruction problems, to help us recover these representations. Okay, so then what's a neural field? Well, a field, we know from physics, is some quantity defined from space and time, or spatial and temporal coordinates. Okay, and so then a neural field is a field that's parameterized fully or in part by a neural network. So let's see what that means. Suppose we had input coordinates x, y, and some measurements of a magnetic field. Well, the neural field would simply take in the x and y coordinates and for that point predict the direction and magnitude of the magnetic field. Or it could be a vector representing the flow within a fluid. The neural network takes in an xy point and outputs again the direction and magnitude of the flow. It could be related to shape. We could take in 3D coordinates and ask our neural network to find the function that describes the distance to the surface of any particular point. This is called a signed distance function. Or it could even be some geospatial data, topographical data, that takes in a latitude and a longitude, for instance. Where this set of techniques came to prominence was in 2020 with a technique that models what is called the Radiance field, or the amount of light traveling in all directions. Once reconstructed, allow us to form new images from novel viewpoints. On the left is a result from the original neural radiance field, or NERF, paper that shows extremely high quality view synthesis, as in rendering the scene from novel viewpoints. This looks like a photograph, but in fact is not any of the original input photographs. And on the right-hand side, we saw the reconstruction of a larger scene from a set of photographs. And this allows us to image and reconstruct whole city blocks. This is the work from NVIDIA called Instant Neural Graphics Primitives that builds upon the neural radiance field method and allows it to be computed much more quickly. We can also apply these neural field methods for representing human beings and producing very detailed shape and appearance of human beings, including things like adapting these to generative models to be able to make new instances of people or, as expected, cats. The applications are not strictly limited, so they could also be used for many different science and engineering tasks, such as topology optimization, tomographic reconstruction, estimating contact dynamics, or even things like astronomical interferometry. Because this is a general framework for solving problems, it can be applied in many ways. And like I said, there's been a huge explosion of these neural field methods just in the past 2 years. This neural radiance field paper that popularized the field came out in 2020. And then since then, there have been many hundreds of papers just on the use of this method because it is extremely effective. Let's take another look at some results from the neural radiance field method. On the left-hand side, we see the virtual renderings of a real-world scene from novel viewpoints. So this scene has been captured with around 30 photographs. And then from then, we asked the neural network to solve an optimization problem to reconstruct the scene. And we see that when we try to estimate the geometry of the scene via its depth, as in how far away each point is, this is on the right-hand side, we get back very high-quality reconstructions from these input photographs. One of my favorite examples of these techniques is from a paper from CVPR this year the Computer Vision and Pattern Recognition Conference. This is called Nerf in the Dark, also from the same authors, Ben Mildenhall and colleagues. Here, the input images are very noisy. They've been taken at night. But the scene that is reconstructed from these photographs can be extremely effectively denoised to produce back these wonderful virtual views without any of the noise that was inherent within the original photograph itself. So I find this extremely impressive. Another application that you might use neural fields for is recovering the surfaces of objects. Work from Ursula and colleagues at the International Conference of Computer Vision last year, called UNISURF, produces these high-quality surface reconstructions of objects within a capture studio. And so different representations, such as these radiance fields or these assigned distance functions, as shown here, can both be reconstructed with these neural field methods. So let's take a slightly more detailed look into how these methods work. We have some sensed image from a camera, typically an RGB image, or it could even be from a depth camera. This we call the sensor domain, and this is what we can actually measure. But we know that these are all in 2D. And what we really want to represent, what we want to reconstruct a representation for, is what we call the reconstruction domain, and here it could be a field of light or radiance, or it could be a distance field to a surface. But this is unknown, and it exists in 3 dimensions, whereas we only have the 2-dimensional input from the RGB images or depth images. And so we're going to set up a problem in which we sample space-time coordinates, x, y, z, t, pass these into a neural network, and ask the neural network to predict at each point in our 3D or 4D space what the value of this radiance field or signed distance field is. Now we have a gap. We have a missing piece. How do we go from this 3D space back to this 2D sensor domain from which the samples from our camera come from? This is where we have what we call the forward map. This is the bridge that joins the 3D space to the 2D space. And when we think about the visual domain, we think about rendering algorithms that turn some representation into a 2D image. And these are differentiable rendering techniques, like volume rendering or sphere tracing, that we can use in combination with an optimization routine. What happens is that the parameters of the neural network are optimized by rendering an image from the radiance field, say, and then comparing the current output to what was sensed by the camera itself. And it turns out that when you couple gradient descent with these neural networks, they are very, very good at solving these ill-posed problems of reconstructing the geometry or the lighting or the material of a scene. Now, we went and wrote a survey or state-of-the-art report on these neural field methods, and this was published at Eurographics. And then we also constructed a tutorial at the CVPR conference, Computer Vision and Pattern Recognition, over the summer this year. And so if you want to know more about these neural field methods, please look towards the CVPR tutorial. We have slides and videos for all of this work, and towards the Eurographics state-of-the-art report, which details many works in this area in many different applications. Okay, so let's go back to the 2 applications I teased you about right at the beginning, which is work that was done by myself and my colleagues. On the left is the output from a time of flight or depth sensor, a camera system like you might find on a smartphone. And we can see that it has noisy outputs in many different areas. The water dispenser is black and low reflectance, and it has a noisy output in the depth image on the left-hand side. Or we have complex reflectance effects like bouncing light off the shiny fridge door. But if you use neural field methods, you can alleviate much of this noise by solving a reconstruction problem to recover a more plausible scene representation. How this works is that we have additional information from the RGB sensor that can be used to alleviate the noise and incorrectness from the time of flight signal. And so we pose a problem in which the reconstruction of the scene must be consistent between the time of flight camera that provides us with some information about depth and the RGB camera, which, as I wave my smartphone back and forth over time, also provides me some information about the depth of the scene via triangulation. Then we use these forward maps to render what we think are images that match the sensed RGB and time of flight images. And then we use these to optimize the parameters of the neural network via a reconstruction loss. Okay, let's move on to our second teased application. In this version, we took 320 photos of this living room and were then able to solve an optimization problem via a neural field that provides these very high quality interactive renderings at arbitrary novel viewpoints within the scene. How do we do this? Well, one problem with neural field methods right now is that oftentimes they can be quite computationally expensive. And so we solve the problem of scalability by introducing a tiling-based system that also resolves the interdependencies between light as it comes from the scene into the camera. You can see the little representations of the tiles here on the right-hand side. I think these are very cute. And with this, we can parallelize the computation to make it easier to compute large-scale scenes at high quality. And we also use this to accelerate rendering itself. Here's an interactive rendering session at 20 frames per second, being rendered on a workstation. Okay, here's some more scene reconstructions. These are all real places that have been reconstructed to a high quality using these neural field methods. And you can see many details like the shiny aluminium door reflection in the bottom left-hand side, or these nice specular highlights in the top left. So we're now able to reconstruct high-quality representations of indoor scenes. Outdoor scenes are still a challenge. Okay, so with that, I just want to end by reminding you of this new and upcoming area in scene reconstruction and more generally in solving inverse problems. So these are called neural fields. If you're interested to know more of the technical details, you can look at our state-of-the-art report or our CVPR tutorial. And I showed you briefly two applications where we can use this to significantly improve the quality of depth estimates that come from sensors, in our case, such as a smartphone, and how we can use this for very high quality, scalable representations that allow us to reconstruct whole rooms of environments to a high quality. All right, thank you very much, and I hope you have a great DCIO.